Good afternoon. Today, here I'll briefly introduce about the how remote sensing can be useful in agriculture with major emphasis on crop inventory and yield modeling. There are dearth of remote sensing related application being evolved in India. Particularly, ISRO scientists and other remote sensing agencies have made extensive efforts to develop and demonstrate potential of remote sensing in various applications related to agriculture. It includes from early development of application using Landsat MSS, NovaHR to currently with the INSAT data. So there are wide variety of application related to agriculture. So here first of all we will see there are different kind of remote sensing potential and for the agriculture. First you can see monitoring of agriculture operation. Today with the kind of data available in the orbit which has got frequent repeativity, particularly with the INSAT satellite which has got even half hourly domain, continuous beaming. This all high repeat satellite data makes it possible to monitor crop dynamics, including monitoring progress of Rabi crops on area, progress of sowing, as well as progress of crop area. And this kind of information is very vital for making decision related to drought assessment, and also you can say with respect to the agro advisory. There is also another application related to agriculture is a crop inventory. Crop inventory includes crop yield estimation, crop area estimation, and crop condition monitoring. So if we have area, that means acreage and yield of a particular administrative unit, you can have production estimate at district level to the state and national level. So it has got immense role, particularly in the crop inventory assessment. There is also another area where crop remote sensing is useful is crop health monitoring. Here monitoring of crop condition, particularly drought affected, drought impacted or drought affected vegetation condition. You can monitor also forewarning, particularly forewarning of the any shortfall in the crop production due to different kind of extreme event, whether it is a drought, maybe a flood, maybe a some cyclonic damage. So these all assessment in the production or shortfall in the production can be assessed with the remote sensing with the kind of multi-temporal data available. Apart from this directly related to the agriculture, there are certain applications on watershed management, command area development, the drainage and irrigation assessment, there is a land degradation and the water quality. So these are the areas which are directly or indirectly linked to the agriculture. Many effort has been made to develop and demonstrate application for its operationalization at different levels. So first of all, we will see what is crop yield estimation and why we need this crop yield estimation. Particularly, crop yield estimation involves area estimation and the yield per unit area. That means productivity estimation. So both multiplying crop acreage with the district level yield, we can get crop production. But question arises in everybody's mind, why we need to have an advanced forecast of crop production. So there are different potential exist for using this for society as well as policy making decision. So one of them is advanced planning. Suppose we are making production estimate which is available well in advance. We can have a contingency measure if there is a shortfall in production is forecasted due to different kind of extreme event or drought, anything, we can have a planning with respect to the contingency measures for improving productivity or improving this. Another, planning with respect to the formulation and implementation of policies related to food procurement. If there is a bumper production or production is surplus, government authority can take decision with respect to export of production, surplus food grain or cotton or sugar, whatever production we are having in surplus, if it is forecasted well in advance, our policy, government can make policy to make export of this. At the same time, if there is a deficient or shortfall in the production forecasted and well and with the more advanced time, then this kind of information can also be useful for procurement of foods to avoid any crisis for the food grain by the people of India. Then third also is a fixing minimum support price. Government fix minimum support price, so based on the availability of forecast estimate on the food grain production or production of any commodity. So if good advance estimate available, it can be useful for the minimum support pricing fixation, and if it is a surplus, some go down, some can be stored in the go down for the fetching higher price. There is also, it is useful for the transport and cold storage establishment, particularly with respect to the perishable goods like vegetable and food crops, in which produce often gets spoiled due to decay in 2 or 3 days if it is not marketed speedily. So this kind of produce needs to be marketed immediately after harvest. So if there is a bumper production or if there is a surplus production and no cold storage available, then these all get spoiled and maybe sometime farmer throw them on the roads. So if adequate storage and transportation facility available, it can be stored, surplus product, perishable goods can be stored, and whenever there is a higher market price available, it can be sold in the market, and that way it can be helpful to the farmer to fetch higher market price. Then also distribution and exportation, export and import. Within interstate, if there is a some region there is a production deficit and some region maybe a production surplus, so some kind of mechanism can be brought in to distribute or to market, distribute and transport from one state to another state this kind of agriculture produce to avoid sudden hike in the price and make to curb the inflation what is realized sometimes in the market and affecting the people of India. So here typically I am not going into detail, but this is a typical reflectors curve which has been used for studying vegetation, including agriculture. So here one can try to understand that how remote sensing, which acquire satellite observation in the different wavelength of the electromagnetic spectrum, so particularly visible, near infrared and the short wave infrared wavelength, which is the optical domain. So you can say optical satellite are useful or being widely used for discriminating different type of crops as well as estimating acreage and production. So here you can see particular visible wavelength, red, because of chlorophyll pigmentation, there is a large scale absorption or you can say strong absorption take place. But just after visible wavelength, there is a sudden rise in the reflectors. This is due to cell wall interface scattering of NIR. So near infrared wavelength gets scattered if there is a healthy cell structure and cell wall. So if it is deteriorated, some kind of stress is there which will lead to the disruption of this cell wall and finally lead to decline in the reflectance within the near infrared region. But beyond near infrared, there are also some water absorption band. 1, 2, 3. These water absorption band, they are linked to the liquid water thickness. If leaf has got more liquid water thickness, that means leaf water potential or leaf water status, it can lead to absorption of short wave infrared wavelength. So some crop like potato, if you see potato leaves and press them, you will find water easily come out. That shows it has got higher leaf water content, and as a result, it can help you to discriminate potato crops. So if you include sphere band while discriminating potato from others, it is definitely going to improve accuracy. Like any kind of crop which has got more leafy thickness, water thickness is more, or you can say more thicker leaves will have more water and can have really a different signature compared to those leaves which have got light and thin leaves. So this is another where one can understand how healthy and stress crop can be separated with the remote sensing. So early in visible wavelength, absorption is more, so reflectance in this visible wavelength, red, green and blue, is less. But when crop is stressed, which leads to the deterioration of chlorophyll concentration, as a result reflectance increase drastically. But in NIR, it is reverse case. If healthy crop is there, reflectance is more because of more scattering at NIR cell wall interface. But whenever it is a stress, maybe it is due to water stress, disease stress, pest stress, or any kind of disorder, that can lead to the rupture of the cell wall and finally decline in the NIR scattering. So reflectance in NIR will be less. Further, in the short wave infrared band, because of water stress or any kind of stress, leaf water content decline. As a result, less absorption of sphere wavelength and more reflectance of the sphere wavelength. So this different response of the stress and the healthy crops to entire electromagnetic spectrum can help you to determine different kind of indices. It may be a normalized difference vegetation index, SAVI, or land surface water index. Land surface wetness indices including normalized difference water index, land surface wetness index. These all can be possible to construct from the because of diversity or because of difference in the reflectance of the stress and healthy vegetation. So different using combination of NIR, red, blue, green as well as sphere wavelength, one can form different kind of indices, and these indices can help you to detect any kind of stress as well as they can act as a proxy for the biomass, crop vigor or stress. Now we will come to our topic, that is how one can separate or one can estimate discriminate crop type. There are different type of crops grown in a different region. In Indo-Gangetic plain, you will find mainly monocrop region like rice wheat system. Rice grown in the Kharif and wheat crop grown in the Rabi season. But there are regions like Maharashtra, Gujarat or some part of this Andhra, where you will find multi-crop region, where in a 1 hectare field you will find 4 to 5 crop. Particularly in Maharashtra, where you will find grape, you find lucerne, you will find wheat, you will find onion and sunflower, all mustard, all crops in the same 1 hectare, means one field. A very small field size is very small. So depending upon the crop type grown in the particular region, those which are dominant or predominant in area are mainly discriminated easily compared to those which are growing in the mixed or multi-crop region. So for crop type identification, one needs to have a principle that based on the fact that each crop having different response in the electromagnetic radiation while interaction of the electromagnetic radiation with the crop target. So there is a response during life cycle. Every crop shows different spectral response in visible, near infrared, sphere or MIR region, and this different response will help makes them different spectrally, which is called spectral signature. So here you can see to the crop and there is a soil. So that is usually soil and crop. In general, they are different. Reflectance curve is different. But here you can see wheat, mustard and sugarcane. There is a distinct difference particularly in the NIR band. This is the reflector spectra which is for the advanced sweeps created during the image acquired during the March. So here particularly you can see sugarcane has the lowest reflectors in NIR, mustard and this. So wheat has got highest because in the mid of February or first week of March, it is in the peak growth stage, very high reflectors in NIR, followed by this sugarcane and mustard is almost harvested. So there are different kind of crop canopy characteristics which influence the spectral signature. So different crops have different kind of canopy architecture, canopy cover, leaf color and composition, phenology. Here phenology means different kind of phenological stage and the basic characteristic which makes them distinguished from using the satellite data. So here leaf color means green color and yellow. If canopy is yellow and green, yellow due to leaf senescence or you can say some decline in the chlorophyll concentration, here will have different kind of spectral response or spectral signature in the visible and near infrared range compared to the healthy crop, as we have seen earlier. And then also phenology, that is a timing of occurrence of event in the life cycle of the crop plant. So different crop grows at different times. So they have different kind of growth pattern at one particular moment of time when satellite data is acquired. So this different kind of growth and its stages exist at particular time helps you to distinguish different crops. Sometimes you will find equivalent growth stage of different crops that really create problems in discriminating crops. At the same time, you will find same crop with the different growth stage in the same. So that also create a problem. So different growth stage or equivalent growth stage of different crops or same crop with the different growth stage is always creating a problem in the improving accuracy. So this kind of variability can be distinguished with the high resolution satellite data to certain extent. Here we understand crop type identification. It is more concerned with the classifying crop types from each other. So we are distinguishing each and every crop from one another, which require more rigorous effort and more authentic knowledge about the crop phenology, its characteristic, and very good ground truth information is required if you have to achieve classifying all crops types within the image window. Another acreage estimation. Acreage estimation is concerned with only few target crops. Here user decides what is his interest crops. If his interest is wheat crop, he will focus on a technique that can help or that can enable him to discriminate wheat from others. Accordingly, he will choose satellite data and acquisition time that helps him to discriminate or distinguish wheat crop from other crop and non-crop cover. So here there are different kind of sensor. IRS sensor has been developed and used for the agricultural application, beginning from the IRS 1A, 1B and 1C, 1D. So there are earlier it was list 2 and list 1 sensor, which has got put stone for the foundation stone for the developing application of remote sensing in agriculture and demonstrated nicely under CAP project. Then with the evolve of advent of this dynamic satellite with the IRS-1C, which having 3 payload, WISP, PAN and LIS-3, it made possible to dynamically monitor agriculture phenomena as well as mapping at high resolution level and field boundary detection. So different kind of agriculture related application from mixed area, like areas with which practice multiple crop region to the homogeneous region, it has become possible to map different crop areas with the sort of sensor which has launched, that is a IRS-1C. Beyond that, then resource set 1, resource set 2, which has got list 4 with the improved partial and multispectral resolution that helps now to cover many other crops. Earlier, it was mainly mustard, wheat, some groundnut, some important crops where you discriminated and acreage estimation were done. But with resource set 1 and resource set 2, more and more new crops, jute crops, other soybean, these different kind of new crops being included for the regular acreage estimation with the improved partial resolution. Particularly onion, where the widely list 4 data has been used for onion crop inventory and other horticulture crop inventory, which has got very minimum extent. So CAPE project particularly it was started in collaboration with the Department of Agriculture and Cooperation for and Ministry of Agriculture and Department of Space. Under this project, several attempts and methodology have been developed and demonstrated for use of satellite remote sensing on acreage estimation. So there are mainly 2 approaches which has been implemented for crop acreage or crop discrimination exercise. One is boundary overlaying approach. Boundary overlaying approach is nothing but here you are superimposing administrative boundary over a satellite data, and all pixel, or you can say all satellite pixel value inside this administrative boundary you are masking out or extracting. Then after ground truth oriented or ground to supervise classification is performed for this block and district level. So this kind of approach which require more ground truth, and it is suitable mainly for the block and district with smaller administrative unit, or you can say it may be more suitable for the research, academic, some demonstrative case studies. But when interest is nation, state or a region, stratified sample segment approach is viable and more extensively used. So this why? Because list 3, which has got swath of 141 kilometers somewhere, and then with the spatial resolution of 23.5 meter, this with the such kind of spatial resolution and the swath, you cannot cover on a particular single date whole India or whole state. At the same time, you cannot have ground truth information across nation for the particular season if you intend to estimate acreage of a wheat crop across India. So here one has to take some viable or versatile approach, that is stratified sample segment approach, which involves stratification of based on the various criteria. First, whole country, or you can say whole state, to be divided into a different kind of strata. These strata are based on agroclimatic region, or it may be based on the historical crop proportion, based on the previous history of Bureau of Economic Survey, that district level data available. Based on the historical crop proportion, you can divide this data into a less than 30%, 30 to 60%, 60 to greater than 60% wheat crop in a different district within a particular stratum. So 3 strata will be there: 30%, less than 30, 30 to 60, 60 to greater than 60. Then crop condition, there is also agriculture. If you can interpret previous season imagery and derive what is the agriculture crop, how much agriculture crop are there, high, low, medium, different data you can produce based on the satellite imagery of previous year. Second, these sample segments, what you choose, it should be only 10%. A random selection of sample segment, it may be 10 by 10 kilometer, 7.5 by 7.5 and 5 by 0.5. So here, if particular state or region where you wanted to estimate acreage is more heterogeneous, it is always advisable to go for higher segment where small segment size. If region is more homogeneous, one should choose coarser sample segment size. Then the sample segment that should be 10% and it is suitable for large area. So here you can see one demonstrative case study of boundary layer approach. Here this is a Kolhapur Tehsil where satellite least 3 imagery is acquired and administrative boundary is overlaid over this. So this is a one Tehsil, Kolhapur Tehsil. Using Kolhapur Tehsil administrative boundary, satellite image, particularly FCC, is extracted. Then after ground truth corresponding to the same season was collected, and based on the ground truth, crop signature were marked on the satellite image, and computer algorithm, particularly MXL, maximum likelihood classification algorithm, is driven by that ground truth. Then training statistic was generated, and finally classification was carried out based on this supervised classification algorithm. So here attempts were made to classify sugar, sunflower, rice, different kind of crops. So there are 4 or 5 crops is possible to discriminate within this particular Kolhapur Tehsil. There is also one more display that whole India, whole Haryana, where we have used or we have tried to demonstrate advanced risk data and its usefulness for the crop classification. So this is Haryana where dominant, it is a homogeneous region where there is a synthetic field size is more than almost you can say 1 hectare or 2 hectare. So you can easily resolve this high homogeneous area or homogeneous land parcel with the particular crop with the coarse resolution satellite data and single date tool. So here same boundary layer of overlaying approach was also tried with the advanced risk data to discriminate mustard, wheat and sugarcane crops. So here also the accuracy assessment for the wheat crop. So before going into detail about this stratification mainly done based on the agroclimatic zones, historic crop proportion and yield levels. Another also maybe previous season health condition, agriculture situation or agriculture area in the previous season imagery. So stratification based on the different kind of criteria. So here you see the one example where sample segment is overlaid over the FCC. Then every 5 by 5 kilometer sample segment is extracted And here also you can see over the Punjab, there are the four stratum based on the agroclimatic zones, and then within the stratum some square blocks, they are the only random sample segment, 10%. This random sample segment for which only satellite data acquired and used in the classification procedure. So only 10 by 10 kilometer or 7 by 7.5 kilometer sample segment corresponding satellite images being used for the classification, and then crops, various crops including wheat 1, 2, 3. That means different wheat crop with the different growth stage is possible to discriminate it, and then they are clubbed together to derive acreage estimation for wheat crop. So in the Punjab, all these 10 by 10 kilometer sample segment, first acreage of wheat is estimated, then this is extrapolated as per the stratum crop proportion, that what we have identified in strata, that less than 30%, greater 30 to 60%, and greater than 60%. So after this sample segment classified and acreage estimated, it is extrapolated to derive a district level acreage estimation based on the stratum based crop proportion of Indo-Pacific crops. This is another approach, another example of acreage estimation using sample segment approach. First, Haryana, where sample segment is overlaid, then particular 10 by 10 kilometer or 7.5 kilometer, where identification of this mustard crop, wheat crop, different overlaid with identified areas, and it was digitized and marked on the imagery. Then this separability analysis was done, which are the class, how much they are separable. After that, supervised classification algorithm is run to classify different kind of crops, and then this different acreage of the 10 by 10 kilometer or 7.5 kilometer for the particular crop is aggregated to derive crop acreage at the district level. So there is also one another program where nationwide crop forecast is given. So this nationwide crop forecast is mainly based on the coarse resolution imagery, that is the advanced WIPS or WIPS data. So here mainly WIPS data are used, which is useful for the state level for crop acreage estimation, particularly crop like wheat, which is dominantly grown in the Indo-Gangetic plain and some other area of central India and some middle part. So here in this all area mainly where sample segment approach, sample segment, this block you are seeing A, B, C. These are the three type of coverage, 30 to 70% agriculture. This three stratum is there. Within these three stratum, this different A, B, C, that is sample segment with the different kind of crop proportion is selected and used for the hierarchical classification. Here multi-date data, that means multi-date data are used for the hierarchical crop discrimination. So hierarchical procedure means decision rule are to be framed to classify or to discriminate individual crop from other. So this is the area where dominantly mustard and wheat crop is there. So this is the wheat crop and this is mustard. Now here you can see mustard grown, reach to the vegetative growth stage, and then it reach to the flowering stage. So it turns yellow and NDVI goes down. But after that it start podding start, which also add to the chlorophyll concentration and greenness. So NDVI increase and go like this. Then there is a leaf fall and sunation in the mustard crop. So particularly this during flowering stage, NDVI goes down, and but in the case of wheat crop, there is nothing like one dip. So it is growing and then becoming static. So both spectral profiles are different. So if you frame decision rule for the particular date, that like flowering, if there is NDVI is greater than particular threshold here and dip by difference in between this and this and divide by certain threshold, then you can have a very good crop discrimination of mustard crop from the wheat crop. So this flowering stage is more ideal to devise rule for the mustard crop. But in case of wheat crop, one should take 2 or 3 dates decision rule to separate out wheat crop from the other crops. CAPE project many crops, particularly wheat, rice, sorghum, mustard, groundnut and cotton. As of now, major 8 crops are considered and for which acreage estimation is prepared and provided to the user agency. So these are wheat crop, Haryana, different kind of Haryana, Punjab, Madhya Pradesh, Rajasthan, Uttar Pradesh, various methodology being developed and the wheat acreage operational wheat crop acreage is given to the user agency. So various states which are covered under the crop CAPE project. For rice, also main dominant rice growing area like Orissa, Tamil Nadu, and phase 2 also Orissa, Andhra Pradesh and Karnataka, West Bengal is considered. Sorghum also mainly Maharashtra and phase 2 also Andhra Pradesh and Karnataka is considered. So cotton, then Andhra Pradesh, Gujarat, Maharashtra, Punjab, Haryana in first phase and then later it is covered in the majority of state dominantly growing this cotton crop. So these are the crop where operationalized methodology of remote sensing for acreage estimation is practiced and bulletin or district level and state level acreage estimation has been given to the Department of Agriculture and state other stakeholder. So this is one also exercise based on the decision rule hierarchical procedure where whole India level dominant crop, particular rice and wheat, is made to discriminated based on the decision multi-date satellite data. So multi-date satellite data, which data has been used to discriminate dominant crop, particular rice and wheat. Approximate coverage one can obtain crop distribution. Here, okay, this is the earlier we have seen that is the approach of sample segment approach where you can get the district level acreage estimation. But if certain kind of exercise like agro advisory service, all those which require crop distribution. So the rice and wheat kind of crop coverage, major crop, dominant crops can be discriminated with the multiple data and crop coverage can be produced and given to the state user agency if it is useful for the certain kind of contingency measure during drought or some agro advisory service during Rabi season. So what is limitation? Limitation particularly in India is a small field size. India we have on an average 0.2 to 0.3 hectare field size is there. Of course, in the Indo-Gangetic plain, field size, synthetic field size is big, but covering other part of India, field size in totality is less. So small field size hinders applicability of coarse resolution or not coarse resolution, especially the even fine resolution like 23.5 or the 30-meter resolution to make accurate crop discrimination. Large diversity of crops, like if there is a monocrop region, it is easy to discriminate different type of crops. If like Punjab, Haryana, where okay during Kharif season only rice, maybe cotton or another sugarcane, 2-3 crops are grown and they are also in the large patch. So it is easily discriminable but distinguishable also. But some area where okay there are 4 or 5 crops at one instant of time at during particular season you find in the field, then it is very difficult to discriminate these different kind of crops. So there one has to have very improved resolution, improved multispectral and hyperspectral kind of satellite data which can make it really possible to discriminate large diverse crop or confusing crops. Large field to field diversity in sowing culture. In India, sowing time window is varying a lot. For particular like wheat crop in Haryana, Punjab, even it is a 30 days. But in some other region, it may go up to even 45 to 60 days from first sowing of first wheat crop to other last end of sowing in a particular region. It may be takes 45 days. So because of this variation in sowing time, which leads to the variability, large scale variability in the crop growth stage at the time of satellite data acquisition for the crop discrimination. So at one particular moment of time across the region, you will find same crop with a different growth stage. So same crop with the different growth stage lead to the different kind of spectral signature and finally add to the spectral confusion. So this spectral confusion is very difficult if we do not have adequate information about the individual crop information. Practice of intercropping, mixed cropping. Like there are certain crops which grow in the row arrangement, like intercrop. Certain crops which are mixed, seeds are mixed and thrown on the field. So see, this kind of intercropping situation where two or more crops are grown in the row is difficult to distinguish because our right now kind of available spatial resolution of 1 meter even cannot discriminate this intercropping because it is a very small row arrangement, some systematic row arrangement is there, but even though it is difficult with the kind of available spatial resolution and multispectral resolution satellite data. High cloud coverage during Kharif crop season. Particularly, we have staple crop in the form of rice, which is practiced or grown during Kharif season. So if we want to have accurate rice acreage estimation, we need cloud-free satellite data. Optical satellite data covering visible, near infrared, short wave infrared domain, highly sensitive to the cloud. And you won't get cloud, you won't able to see crop through images, through cloud by satellite images. So here some kind of data like microwave which have an ability to penetrate or through clouds. So microwave satellite data now available with India has launched or already a research satellite which enables to provide data in the different modes, FRS modes, mono modes. So different kind of partial resolution data is available nowadays. So this can helps you to detect or you can say discriminate Kharif crops. But all reset, it is a data with the very poor repeativity. So it is very difficult to discriminate crop like other than sorghum, maize, many other crops which has got different architecture, different biomass with the soil moisture background, without the water background. So this even reset and this other kind of microwave data usage in the discriminating some challenging crop like this sorghum, maize, pearl millet is really a challenging task. But rice, of course, because of water background and in transplanting stage, you can have a volume scattering. Then during the vegetative stage, you can have a specular scattering, then volume scattering during vegetative stage. So it is different growth stage with the water background can help you to detect or discriminate rice crop easily. So with the microwave data, it is now operationalized methodology available for estimating acreage across nation. Sensor characteristics, these are the factors also influenced like radiometric resolution, ability to record gray level intensity. And so if radiometric resolution is 8 bit, 10 bit, if 10 bit data is there, then it really clear, give distinct, you can have more ability to distinctly differentiate different feature in the satellite images. Like spatial resolution also, if like some certain kind of crop, monocrop region where you require high spatial resolution data, number of band spectral width, sometimes as I said earlier, like certain crops which has got more water content in the leaves. So if you include kind of swirl band or band, that can definitely improve classification accuracy or crop discrimination accuracy. Time of acquisition of satellite image for the crop acreage estimation is equally important, particularly as we have seen earlier in the example of mustard and wheat. Where wheat ideal time for the satellite data acquisition is the mid of February to the first week of March, where crop reach to the anthesis stage, or you can say maximum vegetative growth stage. But in case of mustard, when crop turns yellow, that means when it attains flowering stage, it is the most ideal stage if your target crop for acreage estimation is mustard. Atmospheric condition, like okay, in the multi-day data for the nationwide crop forecasting, where atmospheric condition plays an important role. So their different time atmospheric condition are different. So one need to atmospherically normalize condition for using multi-day satellite data for the crop condition. So if atmosphere is condition is similar, then it is definitely very easy to discriminate different kind of crops with the multi-date. Field size, as we already discussed, small field size, that an homogeneous field, big synthetic field size is more, then you can easily discriminate, accuracy is more, you can achieve. But if field size is small and more heterogeneity of crops, you can always one has to compromise with the accuracy. Then environmental factor, also soil condition, also other kind of climatic factor, these all influence the level of accuracy. Then we will come to the yield estimation, where why crop yield estimation, different kind of approaches being evolved. This, as we have discussed earlier, why we require crop yield estimation for planning, pricing, transport, distribution, all these things. But modeling crop yield is really a challenging. Acreage estimation, to certain extent, it becomes nowadays operationalized technology with the remote sensing for users, for giving estimate acreage estimation to the ministry as well as users. But yield, still modeling yield or modeling quantity of agriculture produced per unit area is a challenge, because it is not only depending upon the biomass or vegetation condition, it depends also on the meteorological factor or climatic factor. So here we will discuss different kind of approaches which has been used for the crop yield estimation. In general, crop yield forecasting and estimation system using satellite remote sensing depends on two bases. One is, as we know, satellites have synaptic viewing capability. It provides large coverage and also supply observation at different times. Means it supply repetitively multispectral observation over the growing season, and therefore providing option for the crop monitoring with the partial possible extent. Then the second is there is a strong correlation between satellite derived vegetation indices and the crop parameter. Satellite derived vegetation indices may be used as a proxy for the biomass, crop vigor, photosynthesis, or many. So this the chlorophyll concentration, this the direct correlation between crop parameter and indices really help to evolve or to develop crop yield modeling approach. Over the years in India, scientific community have come out with different kind of yield modeling approach using beginning from statistical to the process based modeling. So there are spectral yield model which takes into care of which further divided into a spectral growth profile approach, then also spectrometeorological approach, spectral yield approach, yield spectral model, then integration of remote sensing and crop growth model. Then also there is a deterministic biomass production model, where nowadays people have started using or making it operational using satellite data derived from the satellite data available from the INSAT or other kind of multi-repeat satellite data. So here one approach what we can see is a crop cutting experiment. So crop one for field scale spectral yield model. Here we have tried to develop a field scale approach using the least 3 satellite images. Least 3 satellite images classified to the wheat crop, and wheat crop area, wheat crop pixel are used to mask NDVI image. So wheat NDVI is generated. Then according to location, we are having a geolocation of the crop cutting experiment. So surrounding 3 by 3 location surrounding the crop cutting experiment, NDVI is extracted, and this NDVI is related against the crop cutting experiment based yield. Then validation is done with the farmer's interview. So here you can see some of the students, okay, who are harvesting crop 1 by 1 meter panel. So they are throwing and then harvesting crops for each and every crop cutting experiment with the geolocation through GPS. Then these are the different crop cutting experiments distributed over the Saharanpur in the UP. Then NDVI image, then crop classified mainly sugarcane, wheat, wheat and other fallow land and all other crops, other non-agricultural land use also. So here you can see different kind of remote sensing based statistical relationship is developed. That is giving a variance, explain variance about 50% only. But when you add soil factor, mainly land productivity index or soil productivity index, it improves to little extent by 55 to 60%. But further, if you add irrigation management by farmer interview or fertilizer, it can still further improve to the 65 to 70%, explaining variance in the yield. So this kind of model which integrate remote sensing, land and management factor really gives more information on at the field level. So here you can see this is a yield map and it is validated with the independent crop cutting site, and you can see this is only 5 quintal per hectare. That means around 15 to 20% error in the yield estimate or residual mean square error is there. So farmers interview and crop cutting estimate both independently used for the validating this algorithm. So such kind of exercise can help to derive field scale estimation and demonstrating methodology of remote sensing for field level estimation. Then there is also single day spectral yield model where historical yield data are related against the historical area weighted district level vegetation index of the specific crop, which is derived from the sample segment approach. Then this kind of district level yield model are used for the forecasting. But as such kind of relationship cannot be used for the crop forecasting unless it is technologically trend corrected. So one need to use technological trend as an additional variable. So here you can see the example of spectral yield model where vegetation index together with technological trend, because over the period of time from 1950 or beyond green revolution, there is large scale increase in the input, irrigation input, fertilizer input as well as varietal development, which led to the dramatic increase in the productivity of most of the food grain and other crops. So there is a linear trend. So this linear trend one has to incorporate along with the vegetation index as a variable to develop more accurate spectral yield model. So these are for different zones of the Haryana, different kind of models developed based on the vegetation index and the yield trend. So there is also biomass production model where photosynthesis, this is a concept based on the light use efficiency concept. It is one of the most widely accepted for quantifying net primary productivity in annual crops. Thus, general drawbacks of this approach is approach is that it does not give you a within season estimate of the crop. So it cannot be useful for the crop yield forecasting, but definitely it gives yield estimation. But simple physics with the availability of satellite data and some few meteorological data, one can implement this kind of approach for the yield estimation. And it has been nowadays operationalized by the MNFCC with the same simple process-based model based on the light usage efficiency concept. So this is light usage efficiency where okay, MODIS and WIS data is mainly used for classification, and MODIS data used for the generating every 8-day NDVI, and based on the ground measurement relationship between the NDVI and FPAR. FPAR, fraction of photosynthetically active radiation, is estimated for wheat crop every 8 day. Then from sunshine recorders or some radiation estimate, if available from the geostationary satellite data, you can use for estimating PAR. Then some constant, crop specific constant, like for wheat crop light usage efficiency, harvest index. This can be collected from the literature of that particular region or agro ecosystem which you are studying. So here you can see how remote sensing can capture the dynamics of wheat crop. Wheat crop is just now okay in the sown, then emergence, greenness is increasing, it is becoming more green. Then here you can see now it achieved the peak. Then again okay started okay senescence, declining in the greenness, and then it is harvested here. So it is capturing the dynamics of the wheat growth. Now for every 8-day image, you can see wheat area which one can map from the advanced wheat data for 8-day, 8-day composite image of NDVI, PAR, corresponding 8-day PAR, and then PAR multiplied by the NDVI is used for the estimating FPAR, and APAR is FPAR and PAR multiply, you will get APAR, and APAR is converted into a biomass based on the light usage efficiency. So you can finally get the yield estimate based on the one is a linear scaling method, another is a equation, empirical equation which is developed between the FPAR and the FPAR measurement and the NDVI from the modes. So this is majority of area you will find in between the 3.5 to the 4.5 ton per hectare. But interesting thing is here is that majority of district remotely sense estimate based on the Monteith approach, this light usage efficient approach, explained within the 10% relative deviation. So it is acceptable accuracy with 90% confidence level of the official estimate. Now fourth is a integration of remote sensing and crop growth model. Crop growth model are the simulation model. They are simply an inbuilt program that simulate the behavior of plant in response to environment and management conditions. In another way, you can put it like they are the mathematical representation of principle and processes governing behavior performance of the plant. So plant growth simulation model physiologically and quantitatively describe response to environment, and they are mainly used for the different kind of activity for agriculture application related to the climate change, identifying optimal strategy, precision agriculture, yield gap analysis, and so on. So plant growth model, they simulate dry matter accumulation, rate of development, photosynthesis, water balance, and nitrogen mineralization. So, and these kind of model are the daily time step. But this model works mainly under the non-optimal, works under the optimal environment condition, which is you will not find on the farmer field. So here you see most critical reason why this model are not applicable for large area region, because they are requiring large amount of soil and crop parameter, which is partially variability of input parameter is not available. Then they often provide inaccurate estimate for non-optimal condition, which is a farmer field condition. So crop growth model, if you want one has to extend or extrapolate to the large region, it needs to be integrated with the remote sensing. As we know, remote sensing can provide actual status of the crop vigor information. So both potential of both technique need to be realized. Remote sensing can use as a derived input for the physiological model and overcome some of these constraints, because they provide actual state, and also these remote sensing data are the discrete time event. They are not continuous, So one need to always integrate discrete data from the remote sensing with the continuous daily time step information available from the crop model. Crop model simulate input, require input basically weather, soil and crop parameter and management. And it simulate different kind of process, as I said, phenology development, photosynthesis, transpiration, dry matter, and output may be biomass, LAI, yield, water use, and there are different kind of models available. The DSET family, which is a suite of different models, Workforce, World Food Studies, Infocrop, EPIC, Oriza, Wheat Grows. These are the different models which has been widely used for the predicting crop yield as well as studying climate change impact on the agriculture. So there are different kind of technique which has been used for integrating remote sensing and crop model. One is a direct comparison of model prediction and remotely sense estimate. So here model is simulate LAI, model simulate evapotranspiration also through water balance. At the same time, one can derive from satellite evapotranspiration and LAI. Evapotranspiration mainly through Sabal or some other kind of energy balance algorithm. So here strategy is to make direct comparison between the model simulated LAI or ET against the satellite derived estimate. Second is the iterative adjustment. So here one need to iteratively refine or modify initial condition, particularly initial soil moisture, initial crop sowing date, or genotypic or phenotypic coefficient, which is given at the start of the simulation of any model. So these kind of in sowing time, initial soil moisture or phenotypic or genotypic coefficient, one can iteratively keep on changing till the remotely sensed estimate, till the model estimate of LAI and evapotranspiration does not match accurately with the remotely sensed estimate. Third, forcing strategy. Here, model are forced. Model, whether it is a cirrus wheat model or cirrus maize or epi or wheat grows, here models within the source code. A model has been asked to simulate leaf area index with the remotely sensed derived algorithm. So model has been asked to forced to use remotely sensed observation of LAI estimated from the simple empirical relationship or some radiant transfer model. And then another radiant transfer, that means canopy reflectors model, is also used as a link between the crop model and the remote sensing. With remote sensing, you can get satellite reflectors and model crop model simulate LAI, which is also again input to the radiant transfer model for simulating reflectors. Radiant transfer model simulate reflectors as a function of leaf optical properties, leaf area index and other things. So if you have got crop model output in the form of LAI, you can input into the radiant transfer model and you will get the simulated reflectors, which you try to match with the satellite based reflectors using the some demerit function or minimize errors. So various study has been made using integrating remote sensing and crop growth model using sucrose model, WAPOS, even wheat growth in India by Sehgal et al. Also some other people have done Oriza and remote sensing. So this is one example where okay, logarithmic relationship between NDI and LAI is implemented within the Oriza source code to estimate yield of rice in India. So there is also another nowadays approach is coming, that is a climate crop modeling, which is useful for the crop yield forecasting early warning system. Here for point scale cirrus, wheat and infocrops have been widely used by the agriculture university and to estimate crop yield. So, but limitation here is the lack of timely and limited availability of weather crop input. When you want to address issue over a large region or scale nation, you need to have a systematic weather input available in real time or in advance. So another dependence on the stochastic weather generator for forecast period. Most of these exercise or study done which used stochastic weather generator for generating the weather input for the period for which one interested to forecast, for remainder period of the forecast period, remainder period of the forecast. So using spatial approach also wheat grows, and this other approach is used in the Mars project, but this also again dependence on the stochastic weather generator for the multiple lead time forecast, advanced lead time forecast. So coarse grid weather input are used, mainly half degree or you can say 1 degree coarse grid weather input are used. But if one can use climate model simulated or downscale output, which is a bias corrected output along with the within the crop model, which will have a definitely a implication for the generating regional crop yield forecast well in advance and develop early warning tool for the food and drought. So here one case study we have done where we have tried to use climate model forecast and AWS data along with the remainder period of the period of the forecast, climate model simulated forecast, and then soil map and remote sensing. So here for the Haryana and Punjab region, where for every 10-kilometer grid, we have created a database of sowing time, initial sowing time, crop coverage, and genetic coefficient, management condition. Then we have tried to run crop growth monitoring system in the Haryana, Punjab. So here for wheat field forecast, some advanced AWS current situation, and for forecast period we took WRF forecast for different time, 45 days in advance, 30 days in advance, like that. Then also similar for partial domain, we also used NSEP data for the current situation and for forecast period from WRF. So this definitely has shown immense confidence to us or potential of the integrating climate and crop model with the geospatial tool for developing early warning system. So here you can see the agreement index has improved a lot with the different kind of forecast weather if you inputted within the crop model. Then particularly at the point scale, accuracy is achieved with the 45 days forecast in advance will give you the highest accuracy with the least RMS is 83 kg. Hardly 4 to 5% error was there, and RMS is decreasing with increasing advanced days in forecast. Means if you are more advanced forecasting, RMS is becoming lower. That means if you are climate model output, which is more partially representative of weather condition, inputting in the model, then it is definitely giving the more regional picture about the weather as a driver. But if you are giving point scale estimate from the weather observatory, which may not be a representative of partially over large 10-kilometer region area, so it is giving lesser accuracy. So more representative weather input over a partial domain, whether it is for 30 days advance or 45 days advance is not important, but it is giving more importantly partially representative weather to the crop model and improving the accuracy of the crop model. So the cropping system also one can do for Rabi, Kharif, summer and Kharif by integrating supervised classification of inventory, crop inventory into a GIS. So here we try to do generate cropping system in the Andhra Pradesh using rice and different kind of crops in the crop rotation practice with the satellite remote sensing data. Then also one can assess with the advanced field data or high resolution data, coarse resolution data, one can monitor the crop vigor condition over a period, which is a very good input for the developing drought monitoring as well as drought assessment technique. Thank you.